Okay, so today we'll go over homework 7, which is the last homework, and we will have midterm next week. So yeah, we won't have anything else on final week. So the final will be on the 10th week. Okay, so yeah, I think today will also be a very quick discussion. Yeah, so uh, is there any question?
Will you have office hours next week before the finals?
Uh, yeah, sure. I will also ask. Well, if needed, I will also push the discussion or the office hour, before Thursday, since yeah, like last time.
Okay.
I will ask professor for that. Yeah,
Okay, thank you.
yeah. Okay. Yeah. So for this homework, basically we just conduct different type of tests. So here we have first kind of test of homogeneity. So basically this is for something like when you see a table, we have K category on the rows. So category on this side, and then J groups on the column. So on the top, we'll have different group. And we let n sub j denote the column sum. So basically that's the total that at the bottom. So basically it's just the sum of each column. So each group, and then a summation over j for x kj. So basically that's the row sum. So for each kj, we sum over rows. So that's the row sum. So n sub j is column sum, and then x kj sum over j is the row sum. Yeah, and we want to test if the sample between different groups, so that's across different column, are from the same categorical distribution. So for each categorical distribution, that will give us like for example, if we have 4 categories, then each categorical distribution would generate 4 numbers, and then they are across each column. So that we want to test for each group across different group, that is across different column, and then inside that column will give us a very similar 4 different number if we have 4 different categories. So yeah, that is the probability of a category on the rows. So of a category that is the same across all groups. So that will give us this the null hypothesis. So K is for one category. So that's one row, and then across multiple group, they share the same probability. So that will give us like the same categorical distribution for each category across different group. Yeah, so that will give us this null hypothesis. This is the notation from the lecture. And yeah, so professor also want you to to state your null hypothesis in terms of the notation instead of using word, even if they share the same meaning. It would be better to use the notation here. Yeah. So that will be the kind of like a to decide it, what kind of data when you see a table to use which kind of test, and then how to set up the null hypothesis. So some trick can be like to check yeah, like professor said, to check whether the column sum is fixed or not, or does it make sense that we have that the column sum is fixed. So yeah, so in our case, each column it's a group. So similar from what we did in the multinomial, we set a sample size. For example, like each group is 1,000, and then for the 4 different group, we will have 4 different number, but the sum will always be 1,000. So in that case, that the n sub j is fixed. So that will be a good way to decide, or that will be an indicator that we can use this test of homogeneity for that kind of data set. And yeah, so and the distribution of the K group, Yeah, so yeah, that column for each group will be based on a multinomial distribution, a multinomial distribution, and we are going to test if all J groups share the same multinomial distribution. Yeah, and here we also have this expected value for the KJ cell will be the n sub j, that the column sum multiplied by the probability of that category. Yeah, so nj is the number at the bottom for the jth group, and then pk is the probability for that entire kth category. So that will be the number, the probability for the entire k group. So that will be n sub j, and then pk will be 1 over n summation over j. So that will be this will be the row sum, and divided by the total number of the sample size multiplied by the column sum, and that will give us 1 over n row sum and then column sum for the j and kth group. So that will give us the expected value for the kj cell. Any question? Okay, then test for independence. So same thing, a table with now we have different categories of a variable one on a row, and different category of another variable on column. So basically it will, well, if not specified, then it will probably look something like that. But yeah, here we have different variables, and inside that we have different category. So I dot is the row sum. We sum whenever you see a dot, that's the sum on that either row or column. So n dot j is the column sum. So we sum across different I. So that's the column sum. And by the definition of independence, so the probability of ij group category will be probability of that entire column for the ith category, and then will be the multiplied by the probability of j. So that's basically just by the definition of the independence. So that will be our null hypothesis. And then in terms of the expected value for the ith j that cell on that table, that will be n will be the total sample size of the entire of your entire data. Pi dot and pj dot come from here because of the independence. It will just be the multiply them together, and that n will be this n here. Pi dot will be xi dot over n, and that xi dot is the column sum. So xi dot over n will be this pi dot. X dot j over n will be the p dot j, and then it will be 1 over n, and then row sum and column sum sample size. So basically the sum of the sample size on that column and sum of the sample size on that row. Well, yeah, so basically just for the ni and nj row and column. Yeah, so eventually you will see that it shares the same formation here, formulation. So that's what the professor meant when he said you will try different result, but you will try different tests, but well, even if you don't specify what the meaning of the test, you will get the same result, because there's test statistic is the same. Yeah. So yeah, even if you started with a different type of null hypothesis, you will end up with the same test statistic, but the meaning of the test statistic may not be the same. Yeah, even if their final formulation is the same. So this is the two formation for these two type of tests. And yeah, here, yeah, since they share the same formulation, so I'll just make one function together for these setting. And yeah, so this function input is the data. I first create a holder with is the same size for data. So maybe for example, like a K by J data set or I by J data set. So I just want to keep the same dimension for that data, and also initialize the chi-square, the test statistic equal to 0, because the test statistic is just observed minus expected square over expected, and then sum across all ij pair. So so yeah, it's the sum. So I just initialize that as a 0, and also define here. The total will be the sum of the data. That will be that the total sample size, and then row sum. So that so if I have I row, then I'll just I number here. If I have k columns, then I will have k a number in this column sum. Basically, this is just extract a number that given a table, the column sum, the row sum on the right at the very right hand side, and then the column sum at the bottom, and then the final total sum at the lower right corner. That is just extract those information from that table. And now here I just iterate for all ij in that table. And row sum of I, column sum of j divided by n. That's just the two number here for each ij pair. To calculate that, that will be your expected value. And then your test statistic will be for that number observed minus expected square over expected. And then sum across all ij pair. That will be your test statistic. Your degree of freedom will always be the dimension of that -1, and then the column, the dimension of the other side -1, and then I'll put all these number here. Any question? Okay, then the second test, McNemar test. For a 2x2 contingency table, we are testing the marginal probability. If the marginal probability is the same, that is our H naught will be like that. That's by for a 2x2 contingency, and then we're testing that. That's also from the lecture slide. And the test statistic will be the off diagonal difference of that square over the sum of the off diagonal element. So yeah, so for this type of test, we will often observe that two category only on the row and the two category on column, and they are very likely to be the same two category, except that they are probably under different setting. And you will see that in this homework. And yeah, so also define the function that is basically just input the data of basically that's rewrite this part here. Degree of freedom always be 1, and then I'll put everything here. Any question? Okay, yeah, so the first problem, we have 8 different category and 2 group. So we want to check that the categorical distribution in this group is about the same as the categorical distribution in here. So even if we have multiple groups, we're basically just checking that the categorical distribution across different groups are the same. Actually, that's the never mind, just ignore what that's if we are going to conduct the test of homogeneity, then that's what we are going to do. But in fact, this is a test of independence. Yeah. So yeah, just ignore what I just said. Yeah. And yeah, so our null hypothesis will be like that. And then just call that function, input that table, and then call that function, and it will be like that. And then the p-value is greater than 0.05, and do not reject the null. Yeah. So yeah, so your choice of test should be depend on the context. And yeah, is there any relation between response? So that's yes and no, and then ethnic group. So well, yeah, if the test is asking if there's a relation, then we are basically checking yeah, if there's relation that between these two well, you can say variables. So then we will just conduct the independence test of independence. So yeah, so that is test of independence. And then we set up the null hypothesis like that. So yeah, you can mention or kind of specify what you meant by this pi ij, and then what the notation that you mean in, that you use here. So I use pi ij for here instead of the pi k1 and across multiple group here. Yeah. So yeah. So make sure you also specify. Well, yeah. First, set up the null hypothesis by the notation, and then give a more kind of like a detailed explanation of what you meant by your choice of notation here. Yeah. And then in this test, we are using the test of independence. And the IJ means all the ethnic group, and then for the jth response. And then we are trying to test if there is a relation there. And then if there isn't a relation, that's the independence, then the probability of this cell will be just the product. And then if there is a relation, then it will not be independence anymore. There will be some other relation. We don't know what that would be, but it is not going to be an independence cases. And for some IJ. So basically, just if there's at least one IJ, then this will be very likely to be rejected. Yeah. So input data set. So this will just give you exactly the same table here. Call the function on this data set. It will give us that the greater than 0.05. Do not reject the null. Any question? Okay, yeah, here it says already test independent. So yeah, same thing, set up the null hypothesis. Yeah, make sure you give a detailed or some introduction or some like explanation on about what you meant by your choice of notation. Yeah, a professor also asked you, told you yesterday to give a more detail like that, instead of using a word like the null is that is there there isn't a relation, alternative is there is a relation. So instead of using the word, use the mathematical notation and then give a brief introduction about what your notation meant. So test of independence, call the function on this data, slightly greater than 0.05, so reject the do not reject the null. For that problem, that is for the test of homogeneity. So we have 4 different drugs on the row. Yeah, so yeah, if you if you see that table, actually this is it has the group on the row and then the category on the column, which is the opposite as what the example show, or what I meant in here. Yeah, but the idea is the same. You can just flip that table and then you'll get the same result. But just recognize that the group is for the different drug, and then the category is that yes or no. And we are testing the distribution of the yes and no is the same across different group. So that's why we want to test the probability of yes across the 4 different group is the same, and the probability of no is the same across different group. And the alternative is that at least one of them is not equal. Input the data. So note that the first column is actually the total number of the entire column in that row. So that also is an indicator for this nj is fixed. If you observe that table carefully, you will notice that the first column will be the total number of patients. So that means that nj is fixed, and then on the second column of that table, it gives you the number of the nausea. So you have to use that one minus that will be the category in the other group. So note that the n sub j is fixed for each of the group drug group here. So you need to minus that to get the number, and then first create your table, and then conduct the test. Do not reject the no. Yeah. For this one, again, this is the category. That's the K, and this is different group. So you have these different week. Yeah, so this is your J and this is your K. I think it's also like a transpose of what we've been using in the lecture. So make sure you identify the week, the group and the category correctly. Set up the null hypothesis. Give an introduction about what the pi means here. Set up, create a table, call the function. We reject the null. For this one, we are, yeah, although it says is there significant between the 3 group, but we don't know whether this number, this number is not going to be fixed, because it doesn't make sense to fix the number of female and male in this category, because the number of the children's can be varied, but this is just the case that we observe at that time, so it doesn't make sense to fix the number on each category, or on each category. So yeah, it doesn't make sense for that. So that is more likely a test of independence. So we set up the probability like that, input the data, and then test, call the function. Do not reject the no. For part B, we have a ratio. So 105 male for each 100 female. So basically, we are just doing a simple Pearson chi-square test. So the null hypothesis will be the probability of female 100 over the sum, because yeah, this is given by a ratio. Per 100 female, you will get 105 male. So this 105 over 100 over the sum, 105 over the sum, that will give us the probability of female and probability of male. And then under the null hypothesis, we want that to be the same, but the alternative is not the same. Yeah. So the information that is given here will be the null hypothesis. Alternative will be not equal to the null hypothesis. And your observed value will be the column sum of this data. So this will be the column sum of the female and sum of the male in your data set. So that's your observed data. And then your your expected value will be the probability of female multiplied by the total number of that data set. So that will be n times p will be the number of female, expected number of females in your data set. And then probability of that multiplied by that will be the expected number of male in your data set. And then basically just observe of female minus expected square over expected, observe of male minus expected square over expected, sum of this ratio there, that will give you the test statistic greater than 0.05, reject the null. Is there a question? That is just what from the lecture. So yeah, that will be a test of homogeneity. So we have 6 different categories for the word choice. A and this, that, without, with, and there are 2 different groups. So now we set up the test. Yeah, so yeah, the 1 and 2 denoted the group here. We want to test the probability of this A are the same. And then for the probability of AN, it's also the same across the 2 different groups. So this is K1, K2 equal for all K, and then the alternative will be at least for one J is not the same. Copy the data from the lecture slides, and then we reject the no. So so that means that the author, we know that there are 2 different authors. So yeah, they do not share the same pattern for their word choice, at least for these 6 words here. Yeah. So aligned with our conclusion, but we're only testing these 2. Problem 7. So yeah, now you will see that the same category here. Yeah, you can see that same category, except one is on previous day, one is on that specific day. So that's what we have here. 2 contingency table, same 2 category on row and column, but they are under different conditions. Yep, so when you see a table like that, it's very likely that we're going to use a McNemar test. And for that, we are testing the marginal probability are the same. And yeah, make sure you denote or explain what your choice of your notation mean. And then create a table, call the function Q2, reject the null. Same category here, different setting. Test McNemar test. Define your the null. Define your interpret your notation. Create data. Call the function. Reject the null. Now we have 2 tables. Yeah. So I actually get this, the meaning of this table wrong at the first time. So male and female refer to the gender of the physician, and then their choice of advice or not advice their patient on quit smoking. Smoker or non-smoker, the status of the physician, and then their decision on advice or not advice their patient to quit smoking or not. Yeah. So the column, the row refers to the gender of physician, status of the physician, and advice or not advice on the patient. And what proportion of male physician were advised. So basically, it's just 75, 78 over some of that. Female advice, so 50 over 50 plus 98, 89. Yeah. So that number over row sum, the first one, that number over row sum, the second one. Independent. Okay. Set up your no and alternative. Define your notation. Call the function, and then for the specific table, independent for the second table. Define the hypothesis. Call the function on the second table. Do not reject and reject. Then adjust the odd ratio. Advice given male and well, yeah, this is the odd, and then if you divided them, that will be your odd ratio. Advice given male, advice given female, conditional on these two. And this odd ratio will be the probability, conditional probability over 1 minus that conditional probability. And yeah, and this one will be the 1-1 entry. So the male and advice, and then you need to divide it by the probability of male. So a joint probability over a marginal probability, that will give you the conditional probability. 1 minus that on the denominator, same thing for the female, same thing for the denominator. And then take the ratio or take the division, that will give you the odd ratio. Same idea here for the different table. And yeah, that's it for today. That's all I have. Oh, yeah, thanks. If there's any question, then have a great long weekend.
I actually do have a quick question.
Yeah, sure.
I know that you've talked about this a lot, so I apologize, but I'm still just a little bit confused. Can you talk a little bit more about like how we know when to use a test of independence versus when we should use a test of homogeneity?
Yeah, sure. For the question, basically, for example, it says whether they are independent or not. That is just an indicator for the independence. And also here, is there a relation between this and that? So that will be another indicator for your choice. So yeah, these are all independent, a test of independence. So we just want to test whether they have relation or not. For the homogeneity, we are, I think the null hypothesis give you a better intuition on that. So yeah, here we have more, we want to test across all different K is category, yeah. So we want to test across all the category, they are the same. But here we are more likely just testing the category of yeah. So here is one sample test. Here is more likely you have two different variables. So we are just trying to check that the category of the first variable and the second jth category on the second variable, they are the same or not. They are independent or not. So that will give you a sense of to check whether you want to use the independent test or the homogenetic test. So you start from the yeah, sir. Go ahead. Yeah.
No, I was just saying that makes sense. Thank you.
Yeah. Yeah. I think the null hypothesis here give you a more intuition about what choice you would like to use. Yeah. And although they have the same formulation, so so you will not get the result incorrect, but probably if you choose different tests, it will give you will use different null hypothesis. That will probably cause some trouble. I mean, in terms of the test, in terms of your exam, but your final result will not be the same. Will still be the same. Yeah. So yeah, make sure. So yeah. So the null hypothesis give you a good sense or intuition to decide which one you want to use. Yeah. Okay. If there isn't any question, I'll just stop the meeting now.
Thank you.
Yeah. Thanks.